Let's forget about all the pieces on a chessboard except for one. We're going to focus on the knight.
For those unfamiliar with the knight, it moves in a very specific way, an L shape. It can move 2 squares by 1, or it can move 1 square by 2. And it can do this in any direction, meaning that a knight here, for example, can move to any of these squares highlighted by an X. What I want to discuss today is a puzzle called the Knight's Tour, and it involves moving the knight around the chessboard using that move, but landing on each square once and only once. This puzzle that's intrigued mathematicians for centuries, including none other than Leonhard Euler, and you can try it for yourself, or if you can't be bothered, keep watching and you'll see here the Knight's Tour is indeed possible, and this is one of the first ones discovered. As we can see, position 64 is where we ended the tour that we just showed you, and this is an example of a closed tour, since we can get from the final position back to the starting position of that specific tour. Now when it comes to closed tours, there's, in the game of chess, 26,534,728,821,064 possible ways to result in a closed tour. Now let us say, for example, we ended our tour over here. Now obviously we cannot get from the ending position to the starting position in one move. This means this is an open tour, meaning it does not loop basically. And there's an incalculable number of possible open tours.
The Knight's Tour is linked to graph theory by treating each chessboard square as a vertex and each knight move as an edge. The goal is to find the Hamiltonian path, which visits every vertex exactly once, representing the complexity of possible paths. This connection highlights the relevance of graph theory in solving mathematical computational problems, demonstrating its importance across disciplines. Think of an 8x8 chessboard as a network of points, where each vertex corresponds to a square on the chessboard. There is a connection between any 2 points if the knight can move from one square to another in one single legal move. The graph representing the 8x8 chessboard is bipartite, evident from using a 2-color scheme like that of a typical chessboard. Each time a knight moves, it transitions to a square of the opposite color, ensuring that all connections in the graph link points of a different colors, making it a 2-colorable graph, fulfilling the requirements of a bipartite graph. A Hamiltonian cycle, necessary for a closed knight tour, where the knight returns to the start, requires visiting each of the 64 vertices exactly once. Finding such a cycle in this bipartite illustrates the challenge of the Knight's Tour. This link it's not just about chess strategy, but also it has significant graph theory concepts, emphasizing the roles of bipartite graphs, Hamiltonian cycles, or Hamiltonian paths in solving this classic problem.